In this concept, we're going to talk about exponential decay and depreciation. So in the prior concept, we talked about exponential growth, okay? Whereas in this case, we'll talk about exponential decay, and the main difference is in the b term of the exponential equation, right? Whereas in exponential growth, the b term had to be greater than 1. In this case, the b term is between 0 and 1, so it's a fraction or a decimal. Okay, for this equation to refer to exponential decay, the b term has to be between 0 and 1. And then, of course, the a term has to be greater than 0. Okay, and exponential decay typically looks like this, so it's an exponential curve that decreases, as you increase in x. So it could look like this, or like this, etc., or like this, etc. Now let's look at some examples. Identify whether the function is exponential growth or decay. Now, again, looking at so this is the a term, right, which is greater than 0, right? So this is good. Now the b term is 1/3, right? So since the b term is 1/3, then the function represents exponential decay, since the base 1/3 is between 0 and 1. Actually, this x should be up here in the exponent. Okay, so this equation refers to exponential decay, again, because the base, the b term, is between 0 and 1. Okay, let's look at another example. The cost of a new car is $32,000. It depreciates at a rate of 15% per year. What is the formula that gives the value of the car in terms of time? So substituting a equals 32, right, in place of the a term, again, this is the initial amount, right? And why did we choose 32 instead of 32,000? Well, again, whatever we get for y, just treat it as, multiplied by 1,000, right? So in this case, you can cancel out the zeros out of the 32,000 and just use the 32, again, just to make the equation simpler. But be careful that the end result you get, you have to multiply by 1,000, okay? So 32 is the starting amount, so a equals 32, starting amount in thousands, and b, the b term, is 0.85. Now, why do we have 0.85? Well, because it depreciates, the car depreciates at a rate of 15% per year. So after 1 year, after each year, you have 85% of its price remaining, right? So you're losing 15% of the price every year, so what's remaining is 85% of the price, of the initial price, which is 32,000. Okay? So here we have, so y equals 32 times 0.85, which is, 85%, converted to a decimal, and then to the x power. Okay? So this is the equation that gives the value of the car in terms of time. Now, we haven't plugged in for x because we were looking for that general equation, right? We haven't plugged in a specific number of years. Now, part B of the example says, what is the value of the car after 5 years? So now we have a specific value to plug in for x, right? So we take this equation and then we plug in 5 for x, right? So plug in 5 in place of x, and then just evaluate with the calculator. So 0.85 to the 5th power, and then multiply by 32, you get 14.198. But remember, this has to be in thousands, so this is essentially $14,198. Okay, so from $32,000, 5 years later, the car became worth $14,198. Okay. Now, the general equation for exponential decay, again, is very similar to the general equation for exponential growth, with the one and only difference being that In exponential growth, whereas you added the rate of growth, right? In exponential decay, you are subtracting the rate of decay. So if you remember, in exponential growth, we had c times 1 plus r to the t, right? Whereas where r was the rate of exponential growth, here we have 1 minus r, where r is the rate of decay, okay, in decimal form. So if I tell you that something is decaying at 15%, again, according to the previous example, you convert it to a decimal, so then you have 0.15, so r is 0.15, so then 1 minus r is 1 minus 0.15 or 0.85. Exactly just like we had in this example, right? So 0, this is where we got the 0.85 from. Okay, hopefully this was clear. So where y represents the final amount, right? So our final amount after the decay or depreciation. C is the initial amount before the decay or depreciation. R represents the rate of decay expressed as a decimal, and T represents time. Okay. Let's look at an example. Let's keep the equation up here so we can refer to it. Let's just remove all this so we have some space. Okay, so in 1994, the sales of music cassettes reached its peak at y equals, very large number, $2,987,300,000. Big chunk of change, right? So sales of music cassettes in 1994 were almost $3 billion. Okay. Since then, cassette sales have been declining since 1994. If the annual percent decrease in sales is 18 or was or has been 18.6%, what would be the sales of cassettes in the year 2009? Okay, so first off, we write what's being asked is that we write an equation to represent the sales of music cassettes, again as a function of years, without specifying a specific number of years yet. Okay, so again, back to our general equation for exponential decay. We have y equals c times 1 minus r to the t. T being time, r being the rate of decay, c being the initial amount, starting amount, and y being the final amount. Okay, so starting amount is 2 billion, very large number, 2,987,300,000, etc. 1 minus r is 1 minus the rate of decay, which is 18.6%. So converted to a decimal, this is essentially 0.186. Okay, so 1 minus the rate of decay is 1 minus 0.186, and then to the power t, which is the number of years. And then so 1 minus 0.186 is 0.814 to the power t, and this is my general equation representing this scenario, which is the decrease in sales of cassettes. Okay, yearly increase in sales of cassettes. Now, part B of the example asks us about the sales of cassettes in the year 2009. So what were the sales? What was the sales value of cassettes in the year 2009, given this equation? So what are we going to plug in? So we have the initial amount, right? We're not going to change that. We have the rate of, decrease in sales, which, is going to be the same. So then we need to determine the number of years, right? So our model, which is this, right? Our model, or in the case that we're being asked to determine, what year it was, right? The year is the year 2009, but our model depends on starting from the year 1994. How is that the case? Well, because we have our initial amount as this, which was the amount in the year 1994. So our model is dependent on 1994. That's the starting date. That's the starting time. Okay, that's when you start counting the years. And then we need to know what the sales are in 2009. So essentially we need the difference between these two dates. Okay, so 2009 minus 1994 is 15 years. Okay, so our time period is 15 years. So our t is 15 years. Okay, again, remember the unit of time on the rate needs to be the same as the unit of time on t. Okay, remember the rate is right. So here the annual percent decrease in sales is 18.6%. So the rate, the time unit in the rate is years, right? Because it's 18.6% annually. So be very careful with this, okay? So for example, if this were given in some other, time unit, let's say days or months or whatever, you would actually have to convert it to years, right? Or you would have to convert the t to whatever the other time unit is for the rate, okay? So the time unit in these two quantities have to match. The time units, the two time units have to match. Okay, so be very careful with this. This can be a source of a very nice trick on the exam, on the SAT exam. So 15 years, right? So 0.814 to the power 15 we can evaluate by calculator, and then just multiply by 2, with this very large number. In the end, we get y equals the final amount, the sales of cassettes in the year 2009 is this much. So 136 million, 346,788.20. Okay. Second example. A student buys a new car for $17,000. If the value of the car depreciates 15% per year, what is the value of the car in 4 years? Okay, so again, our general equation for exponential decay, or in this case, depreciation, okay, same thing, is y equals c times 1 minus r to the t power. Okay, so then we substitute the values. So the starting price, or the starting amount, was $17,000. And then 1 minus the rate of decay, right, which is 15% annually, which when converted to a decimal is 0.15. And then we want the value in 4 years, right? So my time period is 4 years. Okay? So again, evaluating by calculator, so 1 minus 0.15 is 0.85, and then to the fourth power, and then times 17,000. We get the final amount as $8,874.11. This is the price, or this is the value of the car after 4 years from the student having first purchased it. Okay, so the car will be worth about $8,874.11, or almost 50% of its original value after 4 years. Okay. Okay, so now again, just to hit the point home for depreciation. So you can use the same formula used for exponential decay to solve depreciation problems. Okay, so like we said, it's the same formula for exponential decay and depreciation. Again, it's some initial amount and then multiplied by some rate of decay or rate of depreciation over a certain unit of time, be it a number of years or a number of weeks or a number of months, etc. And again, the unit of time here has to match the unit of time in the rate of decay. And then evaluating all these things together will give you a final amount or a remaining amount from your initial value. Okay, let's look at an additional example for depreciation. So a piece of office equipment valued at $25,000 depreciates at a steady rate of 15% per year, okay, which is 0.15, again converted to a decimal, per year. Okay, what is the value of the equipment in 7 years to the nearest dollar? So again, we write the equation y equals c times 1 minus r raised to the t power. So 1 minus R is 1 minus 0.15, right? My rate of decay. And then the time period is 7 years. And then my initial amount, obviously, was $25,000. And then evaluating by calculator, okay, we get the final amount is equal to $8,014.43. Okay, so this is the value of the furniture after 7 years. Okay, so $8,014 rounded to the nearest dollar. All right, and now we have some exercises. Please pause the video, work on these, and come back for the solutions. Okay, so first exercise, a cup of coffee contains 40 milligrams of caffeine. The average adult can eliminate about 9.5% of the caffeine from their system per hour. Okay, so the unit of time is per hour. So draw a graph to represent the amount of caffeine remaining after drinking a cup of coffee. Okay. So we know that, it's going to look exponential, right? Because here's the rate of decay. So the amount of caffeine, um, so the x-axis is going to be time, okay, as time passes, and then the y-axis is going to be amount of caffeine remaining. Okay, so we're going to start somewhere here at 40 milligrams, right? So this is 40 milligrams on the y-axis, right? We're going to start here at time equals 0, right? And then we're going to start counting, and as we count, there's going to be this decay, by 9.5% over time. Okay? So this is what it's going to look like. Okay? Part B, estimate the amount of caffeine in an adult body 2.5 hours after drinking a cup of coffee. So again, we start with our equation for exponential decay. So C times 1 minus R to the T, right? So the initial amount is 40 milligrams, right? We could write the unit or we could not, either way is fine. But just remember that whatever you get for Y is going to be in milligrams, right? It's going to be the amount of caffeine. So 40 times 1 minus, what is the rate of decay? Well, it was 9.5%. So when converted to a decimal, that is 0.095, okay? And then this rate of decay was per hour, right? Per hour. And then we need to determine the amount of caffeine after 2.5 hours. So my time up here is going to be 2.5, right? Same unit, same time unit in the time variable as well as in the rate variable. Okay. So then I have everything I need now, and then just, evaluating by calculator, you end up getting 31.2 milligrams of caffeine remaining 2.5 hours after drinking the cup of coffee. Okay. Second exercise. A substance decays 20% each day, right? After 16 days, there are 16 milligrams of the substance left. How many milligrams were there initially? So this is asking us in a different way, right? But again, this still this this problem still follows our equation for decay. Y equals C times 1 minus R to the T power. So what do we have? We have a decay of 20% each day. So we know that our R is 0.2, right? We have 16 days that have passed, right? So again, 20% per day and 16 days, same time unit. And then we have, after 16 days, there are 16 milligrams left. So the amount left, that's the final amount. So 16 milligrams here, right? So Y is 16 milligrams. So what is missing? How many milligrams were there initially? So we need C, okay? So after some manipulation, we can say 16, so we can say that C is equal to 16 over 1 minus 0.2 to the 16th power, right? Which, again, this is very easy to evaluate by calculator, right? 1 minus 0.2 is 0.8. Raise it to the 16th power, and then that's your denominator, and then do 16 divided by whatever you get in the denominator, which in the end gives us C equals 568 milligrams of the substance. And again, we can just round um, to the nearest whole number. Okay, this is it for this concept. See you in the next video.